In this video, we will now focus on one of the most fundamental concepts in thermodynamics, which is energy. Energy is the ability to do work or cause change. And in thermodynamics, the foundation of thermodynamics is energy. Everything we study in thermodynamics will revolve in energy. Energy is the foundation of every concept that we will discuss in thermodynamics. How it is stored, how it is transferred, and how it is transformed. Without understanding energy, it is impossible to fully understand the applications of thermodynamics, just like in engines, power plants, refrigeration systems, or any thermal system. So it is of utmost importance that we first understand what energy is. And energy can exist in many different forms. Maraming iba't ibang form ng energy. Some of the common forms of energy include thermal energy. And thermal energy is related to temperature. You also have mechanical energy. Mechanical energy is the energy due to motion or position. Kinetic energy, energy of motion or the energy possessed by a moving body. You also have potential energy, energy due to the elevation or position of an object or system. You also have electrical energy, magnetic energy, chemical energy, which are stored in fuels and food and are very used in power plants. We also have nuclear energy, the energy stored in atomic nuclei. Although there are numerous forms of energy, they all are equivalent. Because why? Although we have thermal energy, mechanical, kinetic, potential, electric, magnetic, chemical, nuclear, lahat sila ay energy. They are all forms of energy. Magkakaiba lang sila ng form. So, that's why in thermodynamics, we will study how thermal energy can be converted to mechanical, how potential energy can be converted to kinetic energy, how electric energy can be converted to mechanical energy, and so much more. That's where thermodynamics revolves. And energy can be converted from one form to another, as we've always said from our introduction, but the total amount remains conserved. So we have what we call the total energy. It is the sum of all the energies in a system. You must remember that. And when we say specific energy naman is the total energy of a system on a unit mass or energy per unit mass. So this means whatever energy we're dealing with, we will just divide it by the mass because it's per unit mass. Let's say we have potential energy. Potential energy has the formula of mass times gravitational acceleration times the height. And when we say specific potential energy, for example, it should be per unit mass. So the mass cancels out, leaving us with G times the height. That's just an example. We have different types of specific energy, specific kinetic energy, specific potential energy, specific internal energy, and so much more. Because at thermodynamics, most of the calculations require it to be per unit mass. And total energy can be divided into groups. We have what we call macroscopic and microscopic. So it's very important that we define the difference of these. Macroscopic forms of energy are those energy that a system possesses as a whole with respect to some outside reference frame, such as kinetic and potential energies. So macroscopic forms, some of the examples are kinetic energy due to motion and potential energy. These energies depend on the system's velocity and position relative to some outside reference. Yun yung macroscopic energy. It depends on the system's velocity and position relative to some outside reference, or what we call the surroundings. It depends on those. So, on the other hand, we have microscopic forms of energy. From the word itself, microscopic, those that are related to the molecular structure of a system and the degree of the molecular activity. So they are independent of outside reference frame. If macroscopic depends on the outside reference frame, microscopic forms of energy does not depend on the outside reference frames or its surroundings. So some example of microscopic energy is internal energy denoted by U. Kasi internal energy is the molecular motion and other molecular stuff happening to a particular substance. It includes molecular motion, molecular vibration, and intermolecular forces. And it is an important property of a substance or everything has internal energy. Again, internal energy, from the word itself, sum of all the microscopic forms of energy. It includes molecular motion, molecular vibration, intermolecular forces, and it depends primarily on the temperature and the phase of the substance, not on its velocity or elevation, contrary to macroscopic forms of energy. Again, let's differentiate macroscopic to microscopic forms of energy. Macroscopic depends on some outside reference frame, while microscopic does not depend on an outside reference frame. Macroscopic is dependent, while microscopic is independent. Example ng macroscopic is kinetic and potential energy, and microscopic is internal energy. Up next, one important thing that we must know is kinetic energy. So what is kinetic energy? From the word kinetic, it means movement. The energy that a system possesses as a result of its motion relative to some reference frame. When all parts of a system move with the same velocity, the kinetic energy is expressed as, take note of these formulas. Kinetic energy is denoted by the capital letters Ke, which means kinetic energy, and it is simply mass times the velocity squared all over 2. It could also be written as 1/2 mass times velocity squared. This is the formula for kinetic energy. And sabi nga natin, kapag specific, this means per unit mass. Per unit mass. So, when we say specific kinetic energy, we simply divide by its mass. So, kinetic energy divided by mass. So, we know that kinetic energy is this, 1/2 mass times velocity squared. So, if you want to make it specific or in terms of per unit mass, simply divide it by the mass and the mass cancels out, leaving us with this formula. this formula. V squared over 2 or simply 1/2 V squared. So, remember this formula for kinetic energy. Mandali naman silang tandaan. Total kinetic energy is 1/2 mass times the velocity squared. And if it's per unit mass or specific kinetic energy, you simply remove the mass because it cancels out. Another important form of energy that we must know is potential energy. From the word potential, it is the energy that a system possesses as a result of its elevation in a gravitational field. When an object or a system is elevated and experiences gravity, it has potential energy. It can be expressed as denoted by the capital letter P, potential, and capital letter E for energy, potential energy. And it's equal to the mass of the body times the gravitational acceleration times the height. From your physics, this is equal to mgh. But in terms of thermodynamics, we will use z to denote the height or the elevation. And g, the value of gravitational acceleration that we will use in our calculation sa thermodynamics are these. For SI, we have 9.8066 meter per second squared. In English, we have 32.174, that is in feet per second squared. And for the CGS system, we have 980.66 centimeter per second squared. Compared to in your physics, we use 9.81 and 32.2. In thermodynamics, we will use these values for gravitational acceleration for a much accurate calculations. And again, just like what we've done in specific kinetic energy, when we say specific potential energy, you just write it in small letters. And again, it's per unit mass. So what is the formula of potential energy? We know that potential energy is mass times gravity times the elevation. And if we want to make it per unit mass, we divide it by the mass. The mass simply cancels out, leaving us with this formula for specific potential energy. Again, m is the mass, g is the gravitational acceleration, and PE is the total potential energy. Pag ginagawang specific, we just write it in small letters. It is very important in our calculations of energy that we are familiar with the different units of energy. We have here joules, Newton meter, BTU or British thermal unit. This is British thermal unit. We also have calorie, and foot-pound. So it's very important that we are familiar with these units of energy. And aside from the units of energy, we must also be familiar with the conversions of energy. You must remember these conversions. 1 joule is equal to 1 Newton meter. 1 BTU is equal to 1055 joules. 1 BTU is equal to 778 foot-pounds of force. And 1 kilocalorie, should be in kilojoules, 1 kilocalorie is equal to 4.186 kilojoules. If it is in calorie, it should be in joules. Again, remember those kasi mahalaga to. In our calculations, we will use these units often. And these conversions will come in handy when we need the units to be uniform. In our calculations, lagi mong gagawing uniform yung units before you proceed. Because if you arrive with the wrong units, most likely the answer you got will be wrong. And up next, the magnetic, electric, and surface tension effects are significant in some specialized cases only and are usually ignored. So in thermodynamics, we will disregard these forms of energy. But in some specialized cases, they will be useful. But they're usually ignored in thermodynamics. And in the absence of such effects, the total energy of a system consists of the kinetic, potential, and the internal energy. So, basically, in our calculation, itong tatlong energy to, yung magiging present. Kinetic, potential, and internal. Again, what is kinetic energy? This is the energy due to motion. The motion of a moving body. Potential energy is due to elevation. When a body is elevated and experiences gravitational acceleration. And we have internal energy, which is due to the microscopic vibrations of a body. And it is expressed as this. Energy is equal to the summation of these three forms of energy. We have internal energy, potential energy, and kinetic energy. In formula form, in most calculations, internal energy is given because every body, fluid, or substance varies. Their internal energy varies, and one major factor is temperature. So it's the value of internal energy is given. But when it comes to potential energy, you'll be given with the elevation and the mass of the body, as well as in kinetic energy, you'll be given with the mass and the velocity of the body. So that's it. On a unit basis, when we say on a unit basis, this is the same as per unit mass. Again, tatandaan, pag sinabi nating on a unit basis, it's just per unit mass. Katulad ng sinabi natin kanina na specific internal energy, specific kinetic energy, and specific potential energy. We just divide each of those with their corresponding mass. So if we divide this by its mass, it will cancel out, leaving us with this. We divide this by its mass, the mass just cancels out, leaves us with this. Alright? Again, on a unit mass basis, it's simply per unit mass divided by the mass. Now we must understand that a stationary system, on a closed system whose velocity and elevation of the center of gravity remains constant during the process. So when we say stationary system, the velocity and elevation of the center of gravity remains constant during a process. The change in the total energy of a stationary system is identical to the change of its internal energy. So they are just identical. The change in the total energy and the change in its internal energy. Mathematically, this means that the change in the total energy is just equal to the change in the internal energy. So this assumption simplifies many thermodynamic analysis. And you must also be familiar with what we call mass flow rate. When we say rate means per unit time. Kanina, when we say specific, if you hear the word specific or on a unit basis, it's per unit mass. But when we say rate, it's per unit time. It tells us how fast something is being done with respect to time. So, if rate is per unit time, mass flow rate tells us the amount of mass flowing through a cross-section per unit time. So, typically sa mga controlled volumes or open system, it typically involves fluid flow for long periods of time, especially in power plants, and it is convenient to express the energy flow associated with the fluid stream in the rate form. So the unit of mass flow rate is kilogram per second in SI, or pound per second in English, and so on. So the formula for mass flow rate is, if you will notice, it is denoted by the letter M with a dot on top. This symbol represents rate. Means it's in rate form. So again, when it's in rate form, it's per unit time. So pag may nakita ka na ganito, tapos may ganyan, it's per unit time. So mass flow rate is equal to the density of the substance or fluid multiplied by, as you can see, V, tapos merong ganun sa taas, that symbol, it indicates it's per unit time. So, because volume flow rate is equal to the cross-sectional area times the velocity of the flow. This is volume flow rate. This one. Again, the mass flow rate is equal to the density of the substance or fluid multiplied by the volume flow rate. So, it's equal to rho times the cross-sectional area times the velocity of the flow. You must remember this formula. Rho is the density of the fluid, A is the cross-sectional area of the fluid flow, and the V is the average flow velocity normal to the area. So remember this formula for the mass flow rate. Again, volume flow rate is also important. It has the formula, as I've said earlier. It has that symbol, and it's cross-sectional area times the average flow velocity. This is the volume of a fluid flowing through a cross-section per unit time. So, in thermodynamics, these are very important because in open systems, they have, it involves flow. Yeah, flow of different fluids that possesses different types of energy. And this is important. Energy flow rate. The energy flow rate has the formula of E is equal to the mass flow rate times the type of energy. So, it's denoted by the capital letter E. And again, it has the symbol like a dot above it to indicate that its rate, it's per unit time. And it is equal to the mass flow rate of whatever fluid or substance times the form of energy associated. Kasi nag-iiba-iba to. Minsan it's potential, it's kinetic, and other forms of energy. So, we must remember this formula. Energy flow rate is equal to mass flow rate times energy. So, there are static forms of energy, and these are the forms of energy which constitute the total energy of a system that can be contained or stored in a system. And when we say dynamic forms of energy or energy interactions, these are forms of energy that are not stored in a system. The dynamic forms of energy are recognized as the system boundary as they cross it, and they represent the energy gained or lost by a system during a process. So, what does this mean? Energy can be classified as static or dynamic. Yan, dalawang classifications. And these classifications is based on whether the energy is stored in the system, whether they are stored in the system, or transferred across the boundary. Static forms of energy are those, again, stored in a system. They are stored in a system. These include what? Internal energy. Internal energy denoted by U. So have kinetic energy. We also have potential energy. And those are types of static forms of energy. Static energy contributes to the total energy content of the system. While on the other hand, dynamic forms of energy, or what we also call as energy interactions, these are energies are only observed only when they cross the system boundary. Recognize the system boundary as they cross it. Yeah. They represent energy gained or lost during a process. So, kapag dynamic forms of energy, we can only recognize them when they cross the boundary of the system. And it's an indicator whether our system lost or gained energy. Another important concept that we must understand is mechanical energy. So, what is mechanical energy? Mechanical energy is defined as the form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device such as an ideal turbine. So, mechanical energy, well, these are the summation of the energy that is needed to produce mechanical work. And one important concept in thermodynamics, especially in open systems, that we must understand as well is flow work or flow energy. So, flow work, what is flow work? Let's read it first. It's the work produced by a force acting on a fluid through a distance. So, what exactly is flow work? Flow work arises because pressure must do work to push a fluid across a controlled volume or controlled surface. And the flow work is given by the formula. Remember this formula because this is very important when we are dealing with open systems, because usually open systems, again, di ba open system, pwedeng pumasok ang mass, pwedeng pumasok ang energy, so there is flow work. And again, ang flow work ay yung energy na kailangan ng pressure para itulak ang isang fluid. When we say fluid, a fluid is a liquid, could be a liquid or a gas. Could never be a solid, yeah. So yun, that's the energy required para itulak ang isang fluid para dumaloy siya. So again, flow work exists only in open system, and remember the formula is the flow work, it's denoted by W sub F to indicate flow work. It's equal to the pressure required to push the fluid and multiplied by the specific volume. Or it is also equal, since we know that the specific volume is the reciprocal of density, we could just substitute this is also equal to the pressure over the density. So this is the formula for flow work. Remember that. So to better understand, let's try to derive it. It's just simple. Again, flow work or the flow energy, workflow, is the energy needed para ma-push ang isang fluid habang ito ay dumadaloy. So, let's say we have an open system. Let's draw an open system. Yan, ganun na lang. We have here our system. And this is the cross-sectional area. Diba? This is the cross-sectional area. It's in the form of a rectangle. and we need to push. Let's say we are going to compress our fluid. So we will apply a certain amount of pressure or force to push our this cross-sectional area where our fluid is contained. Let's say this is our fluid behind the cross-sectional area, and we need to push so that it will be compressed. All right, we need to compress it, so we will move it at a certain distance. It needs to move a certain distance so that the fluid contained in our system will be compressed. So we have here a distance d. This could vary, so we will denote it using delta to indicate change. Delta d. This is the distance we need to push our fluid to compress it. So this is the applied force. So we know that from your physics, work is equal to what? The force applied times the displacement, correct? So that's the formula for work. And we know from our introduction to thermodynamics, pressure is the normal force applied per unit area. But we need the force. So rearranging the equation of pressure, the formula for pressure, cross-multiplying area to there, we could find the force. The force is equal to the pressure times the cross-sectional area. And substituting the force here, we'll arrive with work is equal to the pressure times the area, the cross-sectional area, times the displacement. And again, the displacement is change in distance from the initial to the final. So this can be denoted as delta D. This is our initial and this is our final position. So this is our displacement. So as you can see, this cross-sectional area pushed through that certain amount of distance, that is a volume. So volume, we know that volume is equal to the cross-sectional area times a certain length of that cross-sectional area occupies. So in this case, it is delta D. Kasi nagbabago-bago yung distance or displacement that our fluid will be needed to push on that distance, or whatever process is happening in our thermodynamic analysis. So volume is equal to area times the displacement delta D. So we have, substituting this here, since this is equal to the volume, we will arrive with what we've discussed earlier, that flow work is equal to the pressure times volume. But again, as we've said earlier, in thermodynamic analysis, we want it to be, most likely, most of the time, we want it to be per unit mass. Yes. And we know that volume divided by the mass is what? The specific volume. So that's why we have arrived with this formula. Flow work is equal to pressure times the specific volume, or it's also equal to pressure over the density. Okay, I hope that's clear. So let's proceed. The mechanical energy of a flowing fluid can be expressed on a unit mass basis as E sub mech to indicate that it's mechanical energy. This is what? What is this? This is what we've discussed earlier. This is flow work. This is specific kinetic energy, and this is specific potential energy. This is flow work, this is kinetic energy, and this is potential energy on a unit mass basis. Then the mechanical energy change of a fluid during incompressible. When we say incompressible fluids, the density is constant. So as it undergoes a process, the density does not change. So it becomes this. This is P sub 2 minus P sub 1, which means the final minus initial over the density, plus the V sub 2 squared minus V sub 1 squared, or final velocity squared minus initial velocity squared, all over 2, plus the gravitational acceleration times the change in the elevation, which is denoted by Z sub 2 minus Z sub 1. The mechanical energy of a flowing fluid can also be expressed in rate form. Again, pag sinabi nating rate form, this is what? Per unit time. Must remember that. So, we have here the total mechanical energy. We have again that symbol because it's in rate form is equal to, tulad ng formula natin kanina, which is that energy in rate form is equal to the mass flow rate times whatever type of energy. We have here exactly that. Again, we have our mass flow rate times the three types of energy, which is flow energy, kinetic energy, and potential energy. We've just factored out the mass flow rate. And if we have the change in mechanical energy in rate form, we will arrive with this equation. Again, this is your final initial pressure, final and initial velocity, and the final and initial elevation. It just follows this formula. The mass flow rate is factored out. Yeah. So let's proceed. Forms of energy interactions associated with the closed system. So, let's recall. Pag sinabi natin closed system, ano nga yun? Pag closed system, energy, check, pwede pumasok, but mass, cannot. Okay, malinaw dapat sa atin yan. So, if mass cannot cross a closed system, the only thing that can enter a closed system is energy, and it is in the form of heat. So, we have here what we call heat transfer. Heat transfer. Heat transfer. This is the form of energy that is transferred between two systems, or a system and its surroundings, by a virtue of temperature difference. This is a different topic, but it is very much applicable to thermodynamics. The driving force of heat transfer is temperature difference, because without temperature difference, heat transfer would not facilitate. Again, since closed system, ang pwedeng pumasok ay heat or heat transfer. That's the only thing that could occur, and it's heat is energy as well as work. It is the energy transfer associated with a force acting through a certain distance. Again, for a closed system, mass cannot enter, only heat and work. Remember that. Energy can cross the boundaries of a closed system in the form of heat and work. Yun. Ang pumapasok lang sa closed system ay heat and work. So, heat is energy in transition. It is recognized only as it crosses the boundary of a system. Just like here in this diagram. Again, the driving force of heat transfer is temperature difference. The larger the temperature difference, the higher is the rate of heat transfer. And we have a different topic and subject for heat transfer because heat transfer occurs in many different ways, and there are many things that we must consider in our calculations when it comes to heat transfer. And energy transfer by heat. Since this is energy transfer by heat, we have here what we call adiabatic process. What is an adiabatic process? A process which there is no heat transfer. So, kapag sinabi nating adiabatic process, walang nangyayaring what? Heat transfer. So, there are two ways a process can be adiabatic. May dalawang paraan para maging adiabatic. The system is well insulated so that only a negligible amount of heat can pass through the boundary. So, that's number one. Well insulated siya. Ideal siya. So, walang nakakalabas or nakakapasok na heat. So, the second one, both the system and the surroundings are at the same temperature. Again, as we've said earlier, temperature difference is the driving force of heat transfer. So, kapag walang difference ang temperature ng system and surroundings, there is no heat transfer, meaning it is adiabatic. Heat transfer can happen in three main mechanisms or methods or modes. Just like what I've said, it could happen in three. First is conduction, second is convection, and the third is radiation. These are the three modes of heat transfer, and we have a different subject and discussion regarding these three modes. If the energy crossing the boundary of a closed system is not heat, it must be work. Tulad na sinabi natin kanina, for a closed system, energy is the only thing that could cross the boundary, and it is in the form of heat and work. And sabi dyan, kung hindi siya heat, it must be work. Again, work is the energy transfer associated with the force acting through a distance. For example, a rising piston, a rotating shaft, and an electrical wire crossing the system boundaries are all associated with work interaction. So those are example of work in a closed system. So work is, again, what is work? Energy transfer associated with the work acting through a distance. And we must also know that work done per unit mass is simply work over mass. And one important concept that we must also understand is power. And it's the work per unit time. So, ulitin natin. Work refers to the total amount of energy transferred. This is the total amount of energy transferred. And power naman, on the other hand, refers to the rate of energy transfer. Work is concerned with the amount of energy transferred. Transferred. That's work. While power naman is work per unit time. Power tells us the rate at which energy is being transferred. So, if you could notice the formula, this work per unit time, it tells us how fast work is being done. Again, work is the amount of the total energy transferred, while power is the rate, how fast work is being done. Okay? It is important in our analysis of thermodynamics na magkaroon tayo ng sign conventions in our calculations. Heat and work are directional quantities. Remember this. Heat and work are directional quantities. And thus, the complete description of a heat or work interaction requires the specification of both the magnitude and direction. the sign convention for heat and work. Heat transfer to a system and work done by a system are positive. Katandaan. Heat transfer from a system and work done on a system are negative. To give you a clearer picture, let's look at this diagram. We have here our system chosen, thus region in space chosen for study. This rectangle here represents, and that red line represents our boundary, and the other the external outside our system is the surroundings. Okay, tandaan to. If heat is added to the system here, meaning heat is added or heat goes in our system, that is positive. Oops, lagyan na lang natin dito, positive. Kapag naman heat flows out of the system or our system rejects heat, it's negative. Okay? Now, in thermodynamics, heat is represented by Q. Tandaan, Q. The letter Q represents heat in our analysis of thermodynamics, And work is denoted by the capital letter W. When work enters the system or is done on the system, kaya papasok siya sa system, it's negative. And on the other hand, when work is done by the system or our system produces work kaya palabas siya dyan, this is positive. Again, let's do a bit of a recap. Heat added to a system is positive. Work done by a system is positive. Heat rejected by a system is negative, and work done on a system is negative. Okay? Remember these sign conventions because they are very important in our calculations in thermodynamics. Following a consistent sign convention is critical to arrive with the correct values and magnitude. So, this is specifying the directions of heat and work. So, on our next discussion, we'll proceed with the first law of thermodynamics.